Okay, hi everybody. So let's start the lecture. Today we'll continue the previous topic related uh, to Bayesian linear regression, but we'll consider a more advanced version of the Bayesian linear regression, so-called relevance vector machine. Actually, the relevance vector machine is a more general concept, and it can be used not only with a linear regression model, but also it can be used with classification models, and also it can be used for nonlinear models as well. I mean, the concept of relevance vectors. So let me share the slide. Guys, do you see the slides?
Yes.
Good.
Yes.
Do you hear me well?
Yes, as always.
Good. Okay, so relevance vector machine. Again, this is quite general concept, and it can be generalized to be used not only with linear models, but with nonlinear models as well. First of all, let me remind you some notations related to Bayesian linear modeling. We consider a linear basis function model, which is a linear combination of some nonlinear basis functions. We assume that the parameters of the basis functions are fixed, and the parameters here, these are linear parameters. And we would like to estimate the parameters W. Also, we would like somehow to estimate the number of basis functions to be used with a specific data with a specific data set. As I discussed yesterday, typical basis functions are polynomial, radial basis functions, sigmoid functions. And we assume that the parameters of basis functions are fixed. Maximum likelihood for such model can be described as follows. We assume that that our observation y is generated by the output of the regression model plus a Gaussian white noise. Beta is a parameter of the white noise. And so the predictive distribution of y given x and parameters of the model, it is given by the Gaussian distribution with mean vector mean value equal to f of x w and variance equal to defined by beta. Because all our observations are independent and identically distributed, the joint log likelihood is the joint likelihood is given by the product of Gaussian densities with mean values equal to this and variance equal to this. And so the standard log likelihood is equal to the sum of Gaussian log likelihoods for individual observations. And this is what we discussed yesterday. This is the sum of sum of squared residuals. Okay. And actually, what we want from such models, it's very important for such models to require sparsity. As I told you initially, we don't know how many basis functions we really need. For example, if we consider as a basis function a polynomial of a specific degree, then m is the maximal degree And if that degree is too big, then we can overfit to the data set. And so the predictive ability of the model will be very low. And so we need not only to estimate the parameters W, but also we need to somehow to tune the number of basis functions. Of course, we can do this simultaneously, and we would like the model to be as simple as possible with the same level of error. So this is how, and this can be formulated as additional constraint on sparsity. In our model, we would like the number of coefficients W to be not zero coefficients W to be as small as possible. So we can select M to be quite big, but if many of the coefficients W are zero, then it's okay. To have then it's okay if M is big. And the question is how to achieve this. We can achieve this by imposing some regularization on coefficients W. As you may remember from the course on machine learning, the standard approach to for regularization is to use so-called Gaussian prior. However, the Gaussian prior, that is L2 regularization on coefficients of the model, is not efficient enough to achieve the required sparsity. And one of possibilities is to use the Gaussian regularization, the Gaussian prior, that is L2 regularization, but with different weights for different components of the vector of unknown parameters W. Let me explain. So this is the idea. Imagine that instead of the standard Gaussian prior on a vector of parameters W, where for all parameters W we use the same coefficient alpha to the power -1. Now, for different components of the vector of parameters W, we use different prior hyperparameters alpha sub I. And what does this mean? This means that if we can tune these parameters alpha sub I somehow, then for some of the parameters W, if these hyperparameters alpha sub I is big or is small, then, for example, if it is big, that means that the variance of the Gaussian distribution is very small, almost zero, and vice versa. And depending on this, we can make a decision whether the corresponding parameter W sub I contains some signal, or its non-zero value is only due to noise, and we should penalize this parameter and set it to 0. And if we set it to 0, then this is the same as if we specify the model. And so what is the difference of this formulation with the formulation which we discussed yesterday? The difference is only in how the posterior distribution looks like. Actually, the posterior distribution is of the vector of parameters W given the data set. The posterior distribution is exactly the same. It is Gaussian. And the only difference is here. So yesterday when for all parameters w, we use the same hyperparameter alpha. Here we consider this diagonal matrix with the same value of alpha on the main diagonal. But now, because for different parameters w, we use different hyperparameters alpha sub I, here we have the diagonal matrix with different values of alpha on the main diagonal. This is the main difference. Now let us consider how we can use this and how we can use so-called evidence functional to optimize over alpha and beta to tune these parameters and to sparsify the model. So let me remind you that yesterday I explained that instead of using the standard approach from machine learning, that is cross-validation, to tune the unknown hyperparameters, that is the parameter alpha and the parameter beta, we can calculate so-called evidence function, and we can optimize the evidence with respect to alpha and beta so that without using cross-validation, without using any separate validation or test sample, we can estimate values of these hyperparameters and construct the the Bayesian model. Here we do exactly the same thing, except that now we should tune not the one parameter alpha, but we should tune m parameters alpha. So for each basis function, we have its own parameter alpha sub I. Okay, so this is the evidence function. Again, the evidence function, it is the data log likelihood averaged with respect to the prior distribution of the unknown parameters W. And so it is only the function of hyperparameters beta and alpha. Let us calculate it. And let me explain why if we optimize the evidence function, this can lead to sparsification of the model. So in our case, the prior distribution is like this, and this is the Gaussian distribution. This is the data likelihood written in the vector form. So this is the these are observations, and this is the mean vector of our observations. So this is the matrix of values of basis functions on input vectors xi. This matrix is of size m by m. And we multiply this matrix, regression matrix, by the vector of parameters w. And the covariance matrix here is diagonal because each separate observation has Gaussian distribution and all observations are independent. So this is the log evidence according to the definition. And we can prove exactly in the same way as we did yesterday that log evidence is given by the logarithm of the multidimensional Gaussian distribution with zero mean and the covariance matrix, which is given by this equation. This is the equation. So again, the difference between what we observed yesterday is only in this additional matrix, diagonal matrix here. This is the only difference. And this is the log likelihood of the Gaussian distribution. Okay, and so what we need to maximize these function with respect to parameters alpha and beta. And how to do this? How to estimate these parameters, and why we can get sparseness using this approach. Let me explain you the how to say the technical idea behind the approach. Before going into details, I will first open the presentation from the previous lecture and explain in principle how we can optimize with respect to the parameters alpha and beta. In order you understand the general numerical algorithm behind the optimization. So first, let us consider the case when alpha is just one-dimensional. So for all basis functions, we use the same parameter alpha. And this is the functional from the previous lecture. Here we have the same matrix alpha. So the main difference with the current version is that here we have alpha, which is just a one-dimensional number, and in our case, alpha is a diagonal matrix. Let us denote by phi transpose phi the regression matrix, and by u sub I its eigenvector. It's eigenvector number I. It's obvious that if lambda is the eigenvalue of this matrix, then the matrix A, which is equal to the sum of these two matrices, has eigenvalues alpha plus lambda I. As we know, the determinant of the matrix A is equal to the product of its eigenvectors, right? Of its eigenvalues, right? And so, in order to calculate the derivative of the determinant of the matrix A with respect to alpha, we just need to calculate the gradient. In order to calculate the gradient of the logarithm of the determinant of the matrix, this is the same as to calculate the gradient of the logarithm of the product of eigenvalues with respect to alpha. So it's very easy, and we get this expression. And so what we do? We have this expression which we would like to maximize with respect to alpha. So let us fix beta for now. As I explained you yesterday, we would like to maximize log evidence with respect to alpha and beta simultaneously. So there are two parameters, but we can perform optimization iteratively. We fix beta and optimize with respect to alpha. Then we fix alpha and we optimize with respect to beta, and do this iteratively. And so now let us consider how we can optimize this expression with respect to alpha for a fixed beta. So beta is fixed. So what we get? Let us calculate the stationary point of log evidence with respect to alpha. So I take this expression. Here is it. In this expression, only this term depends on alpha, and this logarithm depends on alpha. And also inside this function, we have some dependence on alpha. Let me remind you how this function looks like. So this function, it is given by this expression, and so only this term depends on alpha. And so what we get, this is the derivative, very simple derivative. And so if we denote, if we move this term with alpha to the left and this term with alpha we keep on the right, we can do the following trick. We can denote by gamma this expression. It's obvious that because in this sum we have m terms, because the matrix phi transpose phi has exactly m eigenvectors and m eigenvalues. So because this ratio is equal to 1 and we sum m values, so this sum is equal to m. And so when we subtract from this term, we get exactly this expression. And so we get that alpha multiplied by the norm of the by the scalar product. So this is the scalar product of the posterior mean vector of parameters with itself. We get this, we get this equation. From this equation, we get that the value of alpha can be estimated using this formula. And so this is how we can make iterations. We make some initial choice for alpha. We use this initial choice for alpha to estimate vector of parameters omega m using this formula. So this is the standard formula from the linear regression, where the matrix A is calculated in this way. Then we estimate the parameter gamma, where the value of lambda is lambda is the eigenvalue of the regression matrix phi transpose phi. Then we re-estimate alpha using this formula, and then we can reiterate. So very simple approach. Actually, we can do the same thing in case of beta. The idea is also very simple. We fix alpha, and now let us perform optimization with respect to beta. This is our eigen vector equation. If we, from this eigenvector equation, it follows that if we differentiate lambda with respect to beta, it is equal to this guy, right? And so we get that the gradient of lambda with respect to beta is equal to lambda divided by beta. And so the gradient of logarithm of the determinant with respect to beta can be calculated in this way. And so it is equal to gamma over beta. So again, we know that because we know that the log evidence is calculated by this formula, and the beta is here, also it is here, and it is inside this term. Then we can calculate the gradient of log evidence and estimate and get the following estimate. 1 over beta can be calculated by using this formula. That's it. And so again, we can perform iterations. So it is so-called iterative optimization. We make an initial choice for beta. We use this to find the estimate of the parameter vector W and gamma, and we re-estimate beta, and then we iterate. This is how we can perform optimization using the structure of the optimization problem, right? So we take this structure into account. And of course, such algorithm converges faster compared to the case when we use the standard stochastic gradient descent. Although this is possible only in case of the Bayesian linear regression, because we use the structure of the log evidence, which we can, for which we can obtain the explicit expression. Otherwise, it's not possible, of course. Any questions so far, guys?
Yes, maybe I have a question. Do initial choices matter here? Like if we first estimate alpha using this iterative process and then beta, and for example, if we switch, will we get different results maybe?
Well, this is a good question. Of course, the log evidence, so let us look at the log evidence. This is the expression for the log evidence. And you see that this expression is highly nonlinear, especially because of this log determinant here. So that means that this function in principle can have several local minima. And the optimization algorithm which I discuss here, it will converge to some stationary point. But nobody guarantees that the stationary point is a global minimum, right? And so because of this, of course, we need some reasonable initialization for values of alpha and beta. And as such, reasonable initialization, because beta is the noise variance value. Beta defines noise variance. In principle, we can perform some preliminary estimate of the noise variance and use it to define the beta. Concerning alpha, so actually alpha is the regularization parameter, and alpha, because alpha to some extent it depends on the numerical so if this regression matrix is ill-posed, alpha should be more or less big, so that the matrix A can be inverted in a numerically stable way. And in order to define alpha, we can use the following trick. We estimate the minimal eigenvalue of this matrix, and we define alpha in such a way, the initial value for alpha, such that this matrix, its minimal eigenvalue is bigger than some threshold. Understand?
Yes, yes.
Okay. Any other questions, guys? Okay, just a second. I'll grab some water and just a minute. Okay, so let us discuss now how we can apply the same approach in case of the relevance vector machine. So now I am so as I discussed, the log evidence function in case of the relevance vector machine can be written in this way. So it's very similar, almost the same, except here we have some slightly different parameterization, but actually this expression is equivalent to the expression on the previous slides. The only difference is that here we use instead of a one-dimensional parameter alpha, here we use a diagonal matrix alpha. But In case we put here a one-dimensional diagonal matrix with the same values of the parameter alpha on the main diagonal, we will get the expression of the locavitance from the previous presentation. So everything is equivalent. Okay, so we need to minimize this function with respect to alpha and beta. And actually, we can use exactly the same trick to perform such maximization. We fix all parameters except one. We calculate the gradient of this expression with respect to this parameter. We get an equation that the gradient is equal to 0. We find the stationary point. That is, for example, we fix all parameters except the parameter alpha sub I. We calculate the gradient of this expression with respect to the parameter alpha sub I. And this is, and then we estimate how this parameter alpha can be defined through all other parameters. And the expression is given here. So the expression is quite simple. Here, the only difference is as follows. So if we denote by omega a posterior value of the vector of parameters, and S is the inverse of this matrix, then in this case, the parameter gamma is defined in this way. So of course the definition is slightly different, but you know, actually it is the same as in the previous case. And so here we have, and so we get the following update equations. And so the algorithm of iterative optimization is the same. We somehow define initial values for parameters alpha and beta, and then we start to update parameters one by one using these equations. Of course, again, of course, the result depends on the initialization. The functional is not convex, and so we cannot guarantee that we converge to the global optimum, but in practice, usually this works quite efficiently. And now the question is, okay, this is the algorithm. Why does it work? Why does it help to sparsify the model, and how we can sparsify the model using this algorithm? And now let me explain this thing. So this is our matrix C, right? This is our matrix C. Because here we have this product of the matrix of basis functions on its transposed version, we can actually rewrite this in this way, where the vector phi I is given just by the values of the basis functions estimated of the basis function number I estimated in different sample points. What we do, we divide this sum into two parts. The first part contains all basis functions except the basis function number I, and the remaining term contains only basis function number I. And so I can represent the matrix C as the sum of the matrix C without the contribution of the basis function number I plus the contribution of the basis function number I. Well, all of us know this, you know, famous Wattbury identity. Also, there is another quite useful identity that if we have two n-dimensional column vectors, then if we calculate the determinant of this matrix, it is equal to 1 plus the scalar product between these two column vectors. This is the standard result from linear algebra. And so what we get, since the matrix C can be represented in this way, we can take this matrix out of the brackets and we get this expression. Then we get that the determinant of this matrix C can be calculated as follows, thanks to this identity, right? This is the first consequence of such a representation. And the second thing, when we calculate the inverse of the matrix C, we get the inverse of this matrix minus this. Okay. So very simple algebra. And so now let me explain why it happens that when we optimize this log evidence function, some of the values of alpha will tend to 0, and some of the values of alpha will tend to infinity. Actually, because here we can, because we represent the matrix C as the sum of C minus I plus some additional term which depends on the basis functions phi I transpose, right? Because we divide the matrix C into two parts in the sum of two terms, we get that these, and because of these two identities here, because of this identity and this identity here, we get that this function L of alpha can be, represented as a sum of two terms. This is the first term, which depends only on all coefficients alpha except the coefficient alpha sub I. And this term depends only on the coefficient alpha sub I. And we can prove, thanks to these two identities, that this term here has the following structure, where these coefficients Si, Qi are given by these expressions. This is a very simple algebra. I'm not going to, to repeat it, but you can do it at home very easily. And so, what is the consequence of such representation? When we perform iterative optimization, we fix all coefficients alpha except the coefficient alpha number I, and we optimize this expression with respect to the coefficient number I. But because of this structure, it's obvious that we optimize with respect to alpha I only this term, because only this term depends on the coefficient number I. Now let us see what happens when we optimize this function with respect to the coefficient alpha I. We when we calculate the gradient of this term with respect to alpha I, we get the following equation, and equate this gradient with respect to 0, and equate this gradient to 0 to find a stationary point. We get this equation. Here is it. And what we get it's obvious that if this term is smaller than this term, then because alpha is greater than 0, this gradient is equal to 0 only if alpha tends to infinity. So the stationary point is at infinity. However, if this inequality holds true, then the corresponding alpha takes some finite value. Here is it. Finite positive. It is some finite positive value, and this happens because the function lambda of alpha can have two patterns of behavior. This is the first pattern, which happens when this inequality holds true, and this is the second pattern, which holds when this pattern holds if this inequality holds true, and this pattern holds if this inequality holds true. And so what does this mean? For any given basis function phi I and associated hyperparameter alpha I, we can compute these quantities Si and Qi. This is true even if optimal alpha is equal to infinity. And so depending on the criterion, on this criterion and the value of alpha, we can then perform the following updates to increase the log evidence. If some basis function is inside the model, and if this inequality holds true, then we just re-estimate alpha. And if this inequality holds true, we delete the corresponding basis function because the optimal alpha should be infinity. And if some basis function is initially outside the model, but if for this basis function we estimate such quantities and it turns that this holds true, then we should add this basis function back inside our model. And here, and so we get the following algorithm. We initialize the value of beta, and all alpha we set to infinity, so the model is empty. We select a function phi I from the set of all available m basis functions, and we compute this value. It is called relevance. If this value is greater than 0, and from the previous iteration we get that alpha is not infinite, we re-estimate alpha. If this value is greater than 0 and alpha is equal to infinity, we add the corresponding model, the corresponding basis function to the model with the updated value of alpha. If this holds true, then we delete the corresponding basis function from the model and set alpha to infinity. And after that, we update beta, we recalculate all Q and Si, these factors, and we iterate. Again, these are expressions for values of S and Q.
Can I ask a question?
Yes, sure.
So we have to calculate m, this q, qi and si. So
Yes.
m of m times so for each I, and for this we need this inverse matrix C minus I inverse. So this seems to be very costly because inverse is like a costly operation, and we have to do it m times.
Yes, this is a very good comment. So actually, of course, if your sample size is like hundreds of thousands, and if the number of basis functions is like, I don't know, hundreds of thousands as well, this method computationally isn't very good. This is true.
But this C minus I, they differ from C by one, by rank, by this rank one addition, and in this case, there's some simpler formulas to.
Yes, this is true. Of course, when we calculate all these inverses, we should use these formulas because this helps. Oh, I'm very sorry. So if we to perform calculations if computational efficiently, of course, we need to use all these equations. All these equations simplifies the recalculation of the matrix C, of its determinant, etc., etc. But still, this method is not, very well, not super efficient if the sample size and the number of basis functions are big.
Thank you.
Okay, now let us consider how it works in practice. So practical considerations. So let us consider so-called kernel regression. So in case of kernel regression, phi of x is given by exponent of x minus, I don't know, some mu squared divided by some sigma squared. And we assume that parameters, and so this parameter mu here, mu I, it is somehow defined. For example, we can put a radial basis function in each point of the training sample. And parameter sigma, it can be just fixed for all, and for all sample points, it is the same. And so let us compare two approaches. As you may remember from the course on machine learning, the support vector regression, it is a special algorithm to construct the regression, which guarantees sparsity by its construction. And only some, when we consider the kernel version, we put a kernel in each point of the sample, and then after constructing the model, only some of these sample points will be, used as support vectors. And so only for these sample points, the corresponding basis functions will stay in the model. For all other basis functions in other sample points, the corresponding coefficients will be equal to 0. And so when we use this noisy sample and construct the model, we observe that like around 29 support vectors are used to construct the approximation. However, when we apply the relevance vector machine, we get significantly sparser model with almost the same level of error. Actually, it is even lower. So in this respect, this is, significantly better solution because we have only 7 support vectors. This is another. These are some interesting results how the algorithm works. So this is our synthetic data, and this is the approximation we get. And of course, we can, and actually we can consider different versions of the algorithm. In the original version of the algorithm, I start from the empty model. So all basis functions are deleted from the model. But actually, I can start from the opposite case. So all basis functions are inside the model. As I already explained, of course, this algorithm doesn't guarantee the global optimum. And so with different initializations, it can converge to different solutions. And this is the example how it works. In this case, what I do, this is the number of the iteration. These are indexes of different basis functions. And here, in this case, I started from the empty model. So all basis functions have zero coefficients. The model is empty. And you see that on different iterations, different basis functions appear in the model. Some of them at some point disappear, but some of them stays till the end, till the convergent. And so we get the model with 9 basis functions. And here I start from the full model. So all basis functions are inside. And I start to increase sparseness by deleting some of the basis functions according to this algorithm. And so you see that at some point I converge to almost the same error, but some basis functions are different and their number is even lower. And so this is the illustration that, okay, the algorithm, there can be several solutions which are more or less equivalent, and we can, achieve we can get these solutions starting from different initializations. Here is another example. So these are some standard data sets used for testing regression methods. The input dimension of these data sets is quite, it's quite different. So like 10, the input dimensionality is equal to 10 to 13. The sample size is not big, of course, because as I told, in principle, such kind of algorithms are very good for middle sample sizes, like up to several thousand, maybe not more than 10,000. Otherwise, it will be too time consuming. And so here we compare different methods for regression construction, support vector machine and relevance vector machine. And we see that on average, a relevance vector machine achieves significantly lower error. And the number of basis functions is also significantly smaller. So relevance vector machine, of course, it's not the strict statement. But according to experimental results, often relevance vector machine allows to achieve significantly sparser results. Another illustration. So this illustration is about computational performance. We take some data set. We either we optimize greedily and delete basis functions, or we optimize with respect to all existing basis functions and delete some of them only at the end of the learning process. Because, okay, on each iteration, we can delete and add some basis function. Or we just put all basis functions inside and don't delete until the end. But we just control the coefficients alpha. And if at the end some of the coefficient alpha are equal to infinity, we delete the corresponding basis functions. And here is the computational performance. So here I depict the sample size. And so time in seconds, of course, this significantly depends on the realization, on the hardware, etc., but still you can understand the typical pattern. And the typical pattern is that in principle, if we optimize greedily and delete basis functions, then the computational performance of such relevance vector machine isn't significantly worse than the computational performance of the support vector machine realized in the corresponding well-known C++ library. So they are comparable given their realizations are done on the same, using the same style of coding, say C++ with good with good programming, using some good programming patterns. What else to say? Yeah, so this is some comparison. Of course, still this relevance vector machine is 10 times slower than support vector machine, but still it's not super big, taking into account the sample size, the standard sample sizes we consider in this case. So practical issues. In practice is usually good to take like 20 to 50 iterations to learn RVM. Usually RVM is from 20 to 50 times slower than ordinary linear regression. Of course, for if we use a kernel, we need somehow to tune the kernel width. And unfortunately, for kernel width, we will still need to somehow to tune it, and the only possibility is to use cross validation. What else to say? Yeah, I think these are no. So that's it. In the remaining slides, okay, I'll briefly discuss other remaining slides. Actually, why I told in the beginning that relevance vector machine is a quite general concept. It's because I can use the same concept not only for regression, but also I can use it for classification, of course, for kernel density estimation, for kernel PCA, and for different methods. So in any method, if I have a basis of some functions like kernel basis, wavelet basis, whatever, I can impose this Bayesian prior, and I can perform adaptive selection of basis functions using the approach I presented. And so this method was generalized to these different types of problems as well, not only for regression. For example, we can perform sparse signal approximation. This is a well-known. There is a well-known approach called matching pursuit algorithm when we add the basis functions one by one. So in each iteration, we select the most relevant basis function to the set of used basis functions and try to approximate the signal as accurate as we can using the constructed set of basis functions. And in this table, we used RVM and compared it with the standard matching pursuit algorithm. And so either the results on the standard Heaviside function, so this is the Heaviside function, is comparable, the results are comparable, or in case we add some Gaussian noise, the results in case of the Bayesian approach based on relevance vector machine is better because we get significantly sparser results. What else to say? We can use these kind of approaches even for image compression. For example, we would like to select which image pixels to keep to represent the image as accurate as we can. And then we impose a prior, a sparse Bayesian prior, as I explained. and then we tune with respect to coefficients in the same way. And this is one of possibility. Of course, in practice, we don't use this algorithm in modern mobile phones or in some modern applications, because nowadays we can use this even more. We can do this even more efficiently by using deep neural networks. But still, this is a good, illustration of the general applicability of this relevance vector machine concept. Okay, what else to say? Yeah, I think this is not so important. That's it, guys. So here, the last several slides are just about usage of the algorithm for kernel density estimation. Again, if we use kernel density estimation, we put a kernel density in each sample point, and we estimate the general data sample density. But in practice, it may be too, we don't need so many kernels in each data point. And so we can select the number, the most important support vectors, support points. And for this, we can use relevance vector machine concept. And on the right, you see the result. So we select only a small number of, so the sample size here is 1000. In each point of this sample, we put a kernel, and of course, computationally, the model is quite, not quite inefficient. But using the relevance vector machine concept, we can select only 49, the most relevant data points, and put Gaussian kernels there, and that's it. We sparsely approximate the kernel density, and the computation, this is very efficient. Any questions, guys? Guys?
Do you recommend to derive everything what was in the lecture at home, because it was quite fast? And for example, for me, I definitely didn't get all the details of the derivation, just some general maybe ideas.
Well, first of all, guys, if I am discussing too fast, please don't hesitate to interrupt me, okay? Second, well, in principle, you can do this. It can be useful, because in homework there will be some problems which are quite similar to what we are discussing here. At the same time, during the seminar, there will be one more discussion about the relevance vector machine topic. So maybe this will be enough for you to understand more technical detail. So it depends. But anyway, the general understanding, for general understanding, yes, some derivation could be useful. But maybe you have specific technical questions, so that I can share the slides one more time, and we discuss them. What do you think?
I think I cannot choose some specific question, just small, like everything, a little bit for everything. So And for example, in the midterm exam, do we need to know how all this done, all these derivations, or
well, there will be right now I cannot say you that there will be exactly a problem where you will need to derive some of such some of such equations. But as you see, the equations, the derivation themselves is not difficult, in the sense that you just need to know some simple matrix formulas, right?
Yes.
So let's see. Right now I cannot say definitely, but yeah, if you spend some time at home, at least looking again through the logic of presentation to understand the main steps. Like, okay, we divide the whole sum into two terms. The second term depends only on alpha I, and the first term doesn't depend on alpha I. We get this expression, we optimize. It has two possible, there can be two possible cases. And so if you remember all these main steps and understand them, I'm sure. And of course, if you remember the main matrix algebra formulas, like the Wadbury identity, I'm sure it should be more or less enough for you to solve the main problems.
Okay, thank you.
Any questions so far, guys? Okay, Nikita, are you here?
Yes, I'm here.
Okay, so I think that we start at 2 o'clock, right?
Yes, let's start at 2
Okay.
o'clock.
Okay. So we start the seminar at 2 o'clock.
Yes.